this lesson is on graphing using derivatives, and before we get into the details of it, I want to clarify finally more about critical points, as I've been promising to do in our past few lessons. In the past few lessons, we said a critical point was a max or a min on the original because the derivative was 0 there. But we're also going to add to that today that the critical point can occur if there is a point there, so the f of c exists, but the derivative does not exist. So this means that we use regular max and mins as critical points, but things like sharp corners and cusps can also be critical points lumped into that category of that particular vocabulary word. So if I'm looking at this graph right here, we have a regular max here where the derivative would be 0, and a min here where the derivative would be 0, and over here at 5 you got a max. And you have two kind of pointy places at 3 and 4. And if you'll read what it says all those are critical points. Okay, all those fall into the category with that vocabulary word, critical points. But of these, 1, 2, and 5 are stationary points, meaning that they're maxes or mins because the derivative is 0. So they're just giving that derivative equals 0 another more specific name. And x3 and x4 are non-differentiable because those are pointy places you can't take the derivative. But again, that is still lumped into the vocabulary word critical point. So critical point carries all of this with it. Okay, so the main part of what we're going to be doing in this lesson is we're going to be sketching graphs where we actually know what the function is. And we're going to be using first what we're calling the first and second derivative tests to get the specific information about those. And so here's our first example. Obviously I say first and second derivative tests. We're going to be taking the first and the second derivatives. So I'm going to come over here and we're going to write the derivative for this. So this is just a nice polynomial here. So we have a derivative of 3x squared minus 3x. What you do for this test is you set that equal to 0 and solve. So if I set this equal to 0, I'm going to solve it. I'm going to factor out a 3x because they have a GCF. That'll leave me with x minus 1. And then obviously you set those equal to 0, so 3x equals 0 and x minus 1 equals 0. So I get x equals 0 and x equals 1. Now think about what we just found. When is the derivative 0? When you have a max, a min, or a flat place on the graph. So this x value at 0 and this x value at 1 are either a max, a min, or a flat place, because we found those by setting our derivative equal to 0. What we're going to do to figure out which one they are is we're going to make a little number line and plot those two things there. And what we do is we test points in each section by plugging those into the derivative and determining whether they're positive or negative. You don't care exactly what the output is, just if it's positive or negative. So the first thing we're going to do is choose something before 0 that's easy to work with and plug into our derivative. And I like to plug into the factor form. You can plug into the original if you like, derivative. So here I am going to plug in like -1 because it's easy. That would give us a -3, which is negative, times a -2, which is negative. And so a negative times a negative is a positive. And so that means anything that I chose before 0 would be positive. Then I choose something between 0 and 1. And again, the nice thing about this is I don't have to know the exact answer. I just have to know if it would be positive or negative. So between 0 and 1, you just have decimals and fractions to choose. So I'm going to choose 1/2. And 3 times 1/2 would be positive. 1/2 minus 1 would be negative. So a positive times a negative would give me a negative. That means everything between 0 and 1 for my derivative is negative. And then finally I choose something over here that is past 1. I could choose 10, 100, whatever, but again I like to use easy numbers, so I'm going to choose 2. So 3 times 2 is positive, 2 minus 1 is positive, and positive times positive is positive. What does this tell me? Well, this goes back to where we were talking about graphs. When the derivative is positive, what do you know about the graph? It's increasing. When the derivative is negative, what's the graph doing? Decreasing. And we know if it changes from positive to negative, you have a max. If it changes from negative to positive, you have a min. So I'm going to come down here and I'm going to write down those things. I know that this is increasing on negative infinity to 0 and on 1 to infinity. I know that it's decreasing there in the middle, which was from 0 to 1. I also know that I have a max where we change from positive to negative, which is at 0, and a min where we change from negative to positive, which is at 1. So I have learned all of that about my graph using this process. And this is our first derivative test. Now we're going to do the second derivative test and basically do the same thing except interpret its answers based on what we know about the second derivative. So I'm going to scroll back up so I have a place to write and do my second derivative. So I'm going to look at this one before I factored it because it'll be easier. And so take my second derivative, I would get 6x minus 3. Again, I'm going to set that equal to 0 and solve. So I get x is equal to 1/2. Now what does that tell me? Well, what do we know when the second derivative is 0? That you have a point of inflection. So this means the original has a point of inflection at 1/2. So I'm going to do a little number line to figure out what the concavity is before and after 1/2. So again, I'm going to pick numbers before 1/2 and plug them into my second derivative, and pick numbers after 1/2 and plug them into my second derivative. So I'm going to pick like 0. 0 is always easy. So 6 times 0 minus 3 would be negative. And then if I picked 1, 6 times 1 minus 3 would be positive. What does that tell me about my original? Tells me that I am concave up, where that second derivative is positive, so that would be from 1/2 to infinity, and that I'm concave down from negative infinity to 1/2. And since it does change sign there from negative to positive at 1/2, I do have a point of inflection at 1/2. Okay, so now what we're going to do is take all of that information and use it to sketch the graph of that function. And so I'm going to make a little graph here. I don't know where it is on the y-axis, so I'm not even going to draw that. I'm just going to say, okay, I know 0 is important, I know 1/2 is important, and I know 1 is important. And so I want to look at what's happening over here. So before 0, I need to be increasing, and I am also concave down. So I put the two parts together about what I know before 0. So I'm increasing and concave down. Based on what I found, I have a max at 0, so I know it's going to change there. I should be decreasing between 0 and 1, and before 1/2, I'm still concave down. So I need to draw this next section as decreasing and concave down. I'm struggling a little bit with that. I'll fix it. So decreasing and concave down. Then, between 1/2 and 1, I'm still decreasing. I fall in that category still, but the concavity changes at 1/2, so I need to be concave up. So I'm still going to decrease, but I'm going to be concave up. I should hit a minimum at 1 and then start increasing again and still be concave up. So it kind of looks like an x cubed graph, but again, we don't know where it is according to the y-axis. We're just doing the general shape of it right now. So we got a little more specific than we were able to before. Okay, so let's move on to another example, and I chose this example because we do have some trig involved and we have to think about our unit circle. And so we want to sketch this function using the first and second derivative tests. And so if I come down here, my first derivative of 1/2 x would just be 1/2 minus, and then the derivative of sine is cosine. And I want to set that equal to 0 and solve. So if I add cosine to the other side, I get the cosine of x equals 1/2. Now, there are many points on the unit circle that have a cosine or x value of 1/2 there. So you have to think about where are some of those places. And I forgot main part of this one. In this type of question, they would have given you an interval. So let's say that they gave us on the interval from 0 to 2 pi. They'll limit you on that. So we want to think about all of our answers that have a cosine of 1/2 on the interval between 0 and 2 pi. So just one time around the unit circle. So those places are pi over 3 and 5 pi over 3. And so that's where I make my number line. So I'm going to put pi over 3, 5 pi over 3 on my number line. Now this time I'm going to do something a little different. I'm going to stick 0 on this end and 2 pi on this end to remind myself that's the interval I'm looking at, and I'm stopping there. I'm just going to draw the graph on that interval. Okay, then you have to test points in this derivative, and you have to remember some of that unit circle stuff again. So if I test something between 0 and pi over 3, for example, pi over 4. So 1/2 minus the cosine of pi over 4. The cosine of pi over 4 is square root 2 over 2. So if you have to, put it in your calculator, 1/2 minus square root 2 over 2. That's going to end up being negative. Okay. Then in the next section, I pick something between pi over 3 and 5 pi over 3. So I'm going to pick pi because that one's an easy one. So 1/2 minus the cosine of pi. Well, the cosine of pi is -1. So 1/2 minus -1 is going to be positive. And then in our last section, I have between 5 pi over 3 and 2 pi. So I'm going to pick 7 pi over 4 because I've already done the math almost, because 1/2 minus the cosine of 7 pi over 4 would be 1/2 minus square root 2 over 2, which is negative because I've already figured that part out. So I have negative, positive, negative there. Now I'm going to list what that tells me. And our first derivative always tells us about where the function is increasing, decreasing, has maxes, or has mins. So if you want to, pause and see if you can write all that down correctly. If not, just follow along. Increasing means the derivative was positive, so that would be between pi over 3 and 5 pi over 3. Decreasing means it was negative, so between 0 and pi over 3, and between 5 pi over 3 and 2 pi. You would have a max where the derivative changes from positive to negative, so at x equals 5 pi over 3. And you would have a min where the derivative changes from negative to positive, so that would be at pi over 3. Now let's go up and do our second derivative test. So our second derivative is the derivative of this right here. So the derivative of 1/2 is 0, so that's gone. And then I have the minus, and the derivative of cosine's negative sine. So I would get two negatives and end up with just a positive sine x as my derivative. And if I set that equal to 0, really, I don't have to add or subtract anything. I just have to think about the places on the unit circle where the sign is 0. And again, the sign is a y value. So we're looking between 0 and 2 pi at 0, pi, and 2 pi. And so on my number line, I'm already marking 0 and 2 pi anyway because those are the ends. But I'm also going to mark pi. And then if we think about things between 0 and pi, and I'm thinking about the unit circle, this one's a little bit easier because the sign is the y value, and everything here has a y value that's positive between 0 and pi. And then between pi and 2 pi, everything has a y value that's negative. So I don't have to think numerically as hard as I did on the first derivative. And so again, remember what this tells you. The positive part of the second derivative tells you that the original is concave up. So we're concave up on 0 to pi. The negative part tells us we're concave down. So we're concave down on pi to 2 pi. And then it does change signs at pi, so that is a point of inflection. So point of inflection at x equals pi. And once you have all that written down, then give yourself some room and draw. Again, I look at all those special points that I labeled on my number lines. 0 is important and 2 pi is important. We're only looking between those. Pi is obviously halfway in there. Pi over 3 is closer to the beginning, and 5 pi over 3 is closer to the end. But that lists out all those special points that we just worked with. So now, in the first section, between 0 and pi over 3, I'm supposed to be decreasing, but I'm supposed to be concave up. So I'm going to draw a part that is decreasing and concave up. Between pi over 3 and pi, I'm in the increasing section and the concave up section. So I'm going to be increasing and concave up. I may have needed to give myself a little more room. May end up drawing over these words here in a second. So between pi and 5 pi over 3, I am still increasing, but I become concave down. So I'm going to draw increasing and concave down. And then between 5 pi over 3 and 2 pi, I'm in the decreasing section, still concave down. So decreasing and concave down. And our max did end up at 5 pi over 3, our min did end up at pi over 3, and our point of inflection ended up at pi. So I've got everything in this graph that I had listed. Okay, our last example I chose, it's a little bit different because it is a rational graph, and you will have a vertical asymptote, and that qualifies as a critical point, and that's going to be a place where the graph can change. You have to actually consider that in your number line. So first of all, where would this have a vertical asymptote? What would make the bottom 0 would be a 0. So you need to keep that in mind, that you have a vertical asymptote at x equals 0. That means when you do your number lines, you will include 0 because the graph could be different on each side of that. You still go through the same process, and so I am going to rewrite this before I take the derivative, because that x squared, because it's just an x squared on the bottom without a plus or a minus, I can put it under each one and reduce so that I would just get x squared and then x to the negative 2. So this is the same as the original. I haven't taken the derivative yet. I'm just making it something that's easier to work with instead of having to do a quotient rule. Now, I'm going to do the derivative. Oh, by the way, you could do the quotient rule if you wanted to. The derivative would be 2x minus 2x to the negative 3. And when I set that equal to 0, I'm going to change this back to a fraction, because anytime you're trying to solve an equation, it's easier to work with fractions and roots than it is negative powers and fractional powers. So I'm going to say that is 2 over x cubed. Then I'm going to add that to the other side. So I'm going to get 2 over x cubed equals 2x. And then I'm going to multiply both sides by x cubed. And so that's going to give me 2 equals 2x to the 4th. Divide by 2. And then when I take the 4th root of each side, so the 4th root, then I get the positive and negative versions of this. So that would be positive and negative 1. It's actually 2 answers. Okay, and again, that was where our derivative was equal to 0, so those are probably maxes, mins, or flat places. I'm going to do my number line, and I'm going to have my negative 1 and my positive 1, but I also have to include that 0 because it's a vertical asymptote. And this is not really standard, but I usually draw like a dotted line when it's a vertical asymptote to remind myself that it's a vertical asymptote, so that I don't call 0 a max or a min when it's really not. And now let's do test points. And so if I do negative 2, I would have 2 times negative 2 would be negative 4 minus 2 over negative 2 cubed, which would be a negative 8 there. And so that would end up giving us a negative for this section. Then if I chose something between negative 1 and 0, like negative 1/2, you might have to get your calculator out, because you would be doing 2 times negative 1/2 minus 2 over negative 1/2 cubed. And again, I just need to know whether it's positive or negative. That actually ends up positive, but again, that might be a place where you have to type it in or do a little scratch work on the side. Between 0 and 1, again, I've got to choose a fraction or something, so I'm going to choose 1/2. Do 2 times 1/2 minus 2 over 1/2 cubed. Again, that's going to be negative. And then finally, after 1, I'm going to choose something easy like 2 again. 2 times 2 minus 2 over 2 cubed, so 4 minus 2 over 8 gives us a positive. So let's list out what we know. Okay, so we're increasing between negative 1 and 0 and from 1 to infinity. We're decreasing from negative infinity to negative 1 and from 0 to 1. When you get to talking about maxes and mins, this is why I put that vertical line there. Because you would normally look at it and say, oh, it changes from positive to negative, so there has to be a max at 0. But it's not a max, it's a vertical asymptote. So there are technically no maxes on this graph. And then your minimums are where we change from negative to positive, and those are not vertical asymptotes. So those actually are minimums. Now let's do the second derivative, which we're using this line right here because it's easier to do derivatives when things are in exponents. So the derivative of 2x is 2, and then the derivative of negative 2x to the negative 3 would be a positive 6x to the negative 4th power. When I set that equal to 0, again, I'm trying to solve, so I'm going to write that as a fraction, and I'm going to subtract it to the other side. Then I'm going to multiply both sides by the denominator to get rid of the fraction. So I'm going to get negative 6 equals 2x to the 4th. I'm going to divide by 2. So negative 3 is going to equal x to the 4th. And then when I take the fourth root of a negative number, I'm in the complex numbers, okay, just like when I take square root, I'm in i's, I'm in those things. So we don't deal with that in this level of our class, so we technically don't have this. All that means is there's not a point of inflection. So don't stress. You still do a number line because you have a vertical asymptote, and that it could have different concavity on each side, but there's not a point where the concavity changes. So if I test something before 0, like -1, 2 plus 6 over -1 to the fourth. Well, the fourth is going to make -1 positive, and so you have a positive plus a positive, which is a positive. And then if you plug in a 1, it's positive, and positive plus positive is positive. So this thing is concave up on both sides of that asymptote, and so you just need to write that. So in summary, what we know from our second derivative test is that we're concave up from -infinity to 0 and 0 to infinity. It's not concave down at all, and there is no point of inflection. So that vertical asymptote does not count as a point of inflection. Now, come down, give yourself some room, and attempt to draw this. So pause and draw. Okay, so we should be decreasing in concave up before -1. We should be increasing in concave up between -1 and 0. Decreasing in concave up before 1 and increasing in concave up after 1 based on everything that we wrote down. Now, obviously, this graph may not have this exact shape, okay, like parabola-wise. We're just meeting the qualifications that we've listed. When you graph this in your calculator, it might look slightly different, but it's going to be increasing and decreasing in the same places. It's going to have the same concavities as what we're sketching. We're going to get more detailed later. Right now, this is what we want to be able to do. So this concludes this lesson.